Our entire observable cosmos was once smaller than a single atom. In less than a trillionth of a second, it expanded faster than light, stretching to a size larger than we can possibly see. This is the mystery of cosmic inflation, a theory that reshapes our understanding of reality itself. By the end of this journey, you will understand how this impossible growth spurt created the blueprint for every galaxy, star, and planet. We will uncover how a quantum whisper could trigger a cosmic roar and confront the startling possibility that our universe is just one bubble in an infinite multiverse. How do you picture the very first moment of everything? That primordial soup was a realm of pure potential, a state of existence so extreme our current laws of physics break down when we try to describe it. Picture all the forces we know today not as separate entities, but as different facets of a single, unified superforce. Gravity, the force that sculpts galaxies, was once indistinguishable from the electromagnetic force that powers our homes and the nuclear forces that bind atoms. In this unimaginably hot and dense state, space and time themselves lost their familiar meaning, becoming a churning, foaming ocean. Quantum fluctuations, which today cause only minor ripples, were the titans of this realm. These random, tiny variations in energy were constantly warping the very fabric of reality, like bubbles forming in that pot of water just before a full, rolling boil. These were not mere bubbles of air, however, but fleeting pockets of spacetime with slightly different properties. Most vanished almost instantly, but one, our universe, found the perfect condition to survive. This entire cosmos was contained within a volume far smaller than a single proton, a seed of unimaginable energy and instability. It was a state that simply could not last, a cosmic spring coiled to its absolute limit. The trigger for its release was a field, a strange and dominant energy that would soon overtake everything. This strange and dominant energy was the inflaton field, the architect of the universe's impossible growth. Think of it not as a substance, but as an invisible landscape of energy that filled every point in that primordial cosmos. This field possessed a bizarre and powerful property. It was trapped in a state of false vacuum, a bit like a marble resting in a small dip on the side of a very steep hill. It wanted to roll down to the true bottom, to a state of lower, stable energy, but it was temporarily stuck. And while it was stuck in this high-energy state, it exerted a tremendous negative pressure. In our everyday world, positive pressure pushes things outward, like air filling a balloon. But negative pressure does something far stranger to the fabric of space. It generates a repulsive form of gravity, a cosmic push that forces space itself to stretch. This was the fuel for the cosmic engine. The universe did not expand because things were flying apart into a void. Instead, the very space between points was being stretched, and it was stretching at a rate that far exceeded the speed of light. This is the crucial distinction that makes inflation possible. Nothing was moving through space faster than light, which is forbidden. Space itself, the stage on which everything plays out, was growing, and that growth has no such speed limit. The mathematics from combining quantum theory and Einstein's general relativity shows that this repulsive gravity, born from the inflaton field's trapped energy, would cause an exponential expansion so violent that a region smaller than a proton would be blown up to a size larger than our entire observable universe in a span of time too short to even conceive. This process explains the remarkable uniformity we see across the cosmos, effectively ironing out any initial wrinkles, yet this expansion was not perfectly smooth. The inflaton field was not a static, placid lake. It was a quantum entity fizzing with tiny, random fluctuations. These minute variations in energy were about to become the most important imperfections in history, the blueprints for everything we see today. This inflationary epoch began when the universe was just 10 to the power of -36 seconds old. That is a decimal point followed by 35 zeros and then a 1. In that first sliver of time, the inflaton field took control, and the universe entered a period of exponential expansion so violent it defies all intuition. This growth spurt was unimaginably brief, lasting perhaps until the universe was 10 to the -32 seconds old. Yet in that fleeting instant, the cosmos swelled by a factor of at least 10 to the 26. To grasp that scale, picture the entire universe before inflation as a single marble. In less time than it takes for light to cross the width of a single proton, that marble would have expanded to a size larger than everything we can observe today with our most powerful telescopes. Why did this need to happen so fast and so early? The timeline is not a random guess. It is the precise solution to deep problems left by the original Big Bang theory. This incredible speed is what smoothed the universe to the remarkable uniformity we see in the cosmic microwave background, and it is why the cosmos appears so flat and geometrically balanced. Because this was an expansion of space itself, not motion through space, it could proceed unimpeded by the universal speed limit of light, and then, as suddenly as it began, it had to stop. The inflaton field could not remain trapped in that false vacuum forever. Like that marble finally finding a path, it rolled down the energy hill, and in doing so, it released all that pent-up energy in a cataclysmic event known as reheating. This was the moment the universe was truly born into the fire of the hot Big Bang, filling the vast, empty space created by inflation with a seething ocean of matter and radiation. The stage was now set for the next great act of creation. This remarkable smoothness presents one of the deepest puzzles in cosmology, known as the Horizon Problem. How can the temperature of the cosmic microwave background be so incredibly uniform in all directions? When we look at one distant part of the sky and then turn to look at the exact opposite part, we see regions that have the same temperature to within 1 part in 100,000. According to the standard Big Bang model without inflation, these two regions should never have met. There simply was not enough time since the beginning of the universe for light or heat to travel from one to the other to even them out. They were forever beyond each other's cosmic horizon, like two ships on an ocean so vast they could never have communicated to agree on a shared temperature. Yet they match perfectly. This is the paradox. Inflation resolves it with breathtaking elegance. Before the inflationary growth spurt, the entire patch that would become our observable universe was tiny, smaller than a single atom. And because it was so incredibly small, every part of it was in intimate contact. Heat and energy could move freely throughout this minuscule region, mixing it into a perfectly uniform, consistent state. It was a single, well-stirred cup of cosmic coffee, all at one temperature. Then inflation struck. In that unimaginably brief instant, it took that tiny, thermally connected region and stretched it to a size larger than our entire observable universe today. The uniformity was not created by the expansion. It was inherited from that initial state and then magnified to a cosmic scale. It is exactly like taking a tiny, perfectly mixed ball of dough and stretching it out until it covers an entire continent. The dough remains smooth and consistent because its uniformity was established when it was small, before the great stretching began. This elegant solution is a cornerstone of modern cosmology, turning a major problem into a powerful prediction. Yet, for all the perfect smoothness this process created, it was not entirely flawless. The quantum fizz of the inflaton field was about to leave its own indelible mark, creating the subtle seeds for all future structure. This geometric perfection presents another profound mystery, often called the flatness problem. Our universe appears to be almost perfectly flat on the largest scales, meaning that the fabric of space itself lacks any significant overall curvature. For this to be true today, the initial conditions of the cosmos had to be fine-tuned to an almost impossible degree. At 1 second after the Big Bang, the density of the universe needed to be balanced to within 1 part in a number with 60 zeros. The odds of this happening by pure chance are so astronomically small, it would be like throwing a dart from one end of the observable universe and hitting a bull's eye just 1 millimeter wide on the other side. This level of precision seems to demand an explanation beyond mere luck. Once again, cosmic inflation provides a powerful and elegant solution. The mechanism of exponential expansion acts like a cosmic iron, smoothing out any initial curvature. Think of the surface of a wrinkled, crumpled balloon. When you start to inflate it, the surface is full of bumps and folds. But as you blow the balloon up to an enormous size, any tiny section of its surface you can look at appears perfectly flat to your eye. Inflation did exactly this to the fabric of spacetime. It took the entire cosmos and stretched it by such an immense factor that any original curvature was stretched out to scales far beyond what we can ever observe. The part of the universe we can see is just one tiny, flat-looking patch on a surface that might be unimaginably large and possibly curved in its totality. This prediction of a flat observable universe has been spectacularly confirmed by detailed observations of the cosmic microwave background, where scientists have measured the geometry of space with incredible precision. The universe we can see is geometrically flat because inflation made it so, solving the fine-tuning enigma by physically forcing the cosmos into this balanced state. Yet this very solution opens up an even grander possibility, that our entire observable universe is just one flat island in a far vaster and perhaps more convoluted cosmic landscape. The most profound legacy of this cosmic stretching is the blueprint it provided for everything we see. Those tiny quantum jitters in the inflaton field, the very essence of its fizzing energy, did not get smoothed away. Instead, they were caught in the act of expansion and stretched to astronomical proportions. Think of drawing a tiny, wiggly line on a deflated balloon. As you blow the balloon up to an enormous size, that tiny wiggle becomes a vast, rolling wave. Inflation did exactly this to the fabric of reality. The microscopic ripples in energy density, dictated by the fundamental uncertainty of the quantum world, were magnified into continents of slightly higher and lower density spread across the newborn cosmos. These were not yet structures but their seeds. The universe was no longer a perfectly smooth sheet. It now possessed a subtle fingerprint of variation, an imprint of quantum noise written across the sky. In the quieter universe that followed inflation, gravity got to work on this blueprint. Regions that had a tiny bit more mass, courtesy of those amplified fluctuations, exerted a slightly stronger gravitational pull. Over billions of years, they drew in more and more matter from their surroundings, growing from faint whispers in the density field into the first stars, the first galaxies, and the vast, glittering clusters we observe today. It is a stunning connection. The same quantum uncertainty that governs the behavior of a single particle also determined the location of every galaxy. The specific pattern of these initial ripples, a prediction made by inflationary theory, leaves a distinct signature. This signature is found etched into the cosmic microwave background, the afterglow of the Big Bang, as tiny temperature variations. And it matches with breathtaking accuracy the large-scale distribution of galaxies in our universe. Every star, every planet, and every cosmic structure we can see owes its ultimate origin to a quantum tremor, stretched to cosmic scales during the universe's first fleeting moment. Einstein's cosmic speed limit remains unbroken because nothing was racing through the cosmos. The staggering velocity of inflation came from space itself stretching. Think of the universe as a vast, rising loaf of raisin bread. Each raisin represents a galaxy, or even a cluster of galaxies, embedded within the dough of space-time. As the bread bakes and expands, every raisin moves away from every other raisin. No single raisin is speeding through the dough. Instead, the dough between them is growing. If the bread were to expand rapidly enough, two raisins on opposite ends could find themselves moving apart faster than any ant could ever hope to crawl between them. The ants in this analogy are like photons, particles of light. They remain the fastest travelers moving through the dough of space, never exceeding their own local speed limit. Yet the overall stretching of the loaf can easily outpace them. This is the precise loophole within general relativity that allows for such phenomenal growth. The expansion rate during inflation was not just fast, it was truly exponential. The scale of the universe didn't just increase, it doubled and then doubled again, over and over in a cascading chain reaction. Each doubling occurred in an identical, minuscule span of time, leading to a final size that is almost beyond comprehension. Since this process involves the creation of new space itself, rather than any object or signal traversing existing space, it does not transmit information from one point to another. There is no paradox, only a profound revision of how we think about motion and distance. The very definitions of speed and separation transform when the stage upon which everything plays is actively growing. This realization forces us to accept that the cosmos operates on rules far stranger and more magnificent than our everyday intuition allows. That faint microwave glow, the cosmic microwave background, is a direct echo from the dawn of time. It is the oldest light we can see, a snapshot of the universe when it was a mere 380,000 years old. Before this moment, the cosmos was a searing, opaque fog of plasma, too dense for light to travel freely. As the universe expanded and cooled, electrons and protons finally combined to form the first atoms, and the universe suddenly became transparent. That first burst of light, released in that instant, has been traveling for over 13 billion years, and we can still detect it today as a cold whisper of microwave radiation that uniformly bathes the entire sky. This cosmic afterglow is a foundational pillar of the Big Bang theory, but its most profound secrets are found in its subtle imperfections. This background is not perfectly smooth. If you could see it with microwave eyes, you would notice a mottled pattern across the sky, a map of tiny temperature differences. Some patches are ever so slightly warmer, others infinitesimally cooler by about 1 part in 100,000. This is the cosmic fingerprint left by inflation. Those quantum fluctuations in the inflaton field, stretched to cosmic proportions, became regions of slightly higher and lower density in the early plasma. Denser regions had more gravity, which meant photons climbing out of those gravitational wells lost a tiny bit of energy, making them appear slightly cooler. Less dense regions offered an easier escape, leaving the photons slightly warmer. This pattern of hot and cold spots is not random noise. Its statistical properties, the specific way these spots are distributed across different angular scales, form a unique signature. The theory of inflation predicts that the quantum seeds it planted should produce a pattern that is nearly scale invariant. This means the fluctuations look statistically similar whether you are looking at a large patch of the sky or a small one. a direct consequence of the exponential stretching. Furthermore, the pattern should follow a Gaussian or bell curve distribution, exactly what you would expect from the random nature of quantum jitters. The most stunning confirmation comes from the detailed spectrum of these fluctuations, which reveals the imprint of sound waves or acoustic oscillations rippling through the primordial plasma. In the first few 100,000 years, the universe was a ringing bell. Gravity would try to pull matter into the denser regions, while the intense radiation pressure would push it back out, creating a regular, oscillating pattern of compression and rarefaction. When the universe became transparent, this oscillation was frozen in place, imprinted onto the light of the cosmic microwave background. Satellites like WMAP and Planck have mapped this pattern with breathtaking precision, and the data aligns perfectly with the predictions of the inflationary model. The cosmic microwave background is more than an afterglow. It is a direct message from the end of inflation itself, a fossilized record of those first, unimaginable moments. It allows us to test the physics of a realm we can never directly observe, providing compelling evidence that our entire cosmic history began with a quantum-fueled, faster-than-light growth spurt. This nearly scale-invariant pattern is the universe's own unique fingerprint, known as the Harrison-Zeldovich spectrum. It tells us that the primordial density fluctuations had roughly the same strength or amplitude, whether they were destined to become a vast supercluster of galaxies or a single, isolated dwarf galaxy. The physical processes that sculpted the cosmos during its inflationary growth spurt were blind to scale. This is a hallmark of a very specific kind of expansion, one driven by an inflaton field that was changing very, very slowly, like a ball rolling almost imperceptibly down a nearly flat plateau. The result is a cosmic blueprint that looks statistically identical whether you examine a billion light-year-wide section of the sky or a much smaller patch. It is as if you took a detailed photograph and found that it remained just as sharp and detailed no matter how much you enlarged it. This prediction was a bold stroke of theoretical genius, made long before our telescopes were powerful enough to check. The exquisite maps of the cosmic microwave background provided the test, and the data revealed a spectrum of fluctuations that matched this prediction with stunning accuracy. Yet the fingerprint is not perfectly uniform. There is a subtle tilt, a slight preference for larger fluctuations over smaller ones. This tiny deviation from perfect scale invariance is not a flaw in the theory, but a treasure trove of information. It tells physicists about the precise shape of the inflaton field's potential energy hill, offering clues to the specific forces that govern the birth of everything. The fact that this prediction was made and then confirmed stands as one of the strongest pillars supporting the entire inflationary paradigm. Now, scientists scrutinize these minute deviations, using them to sift through the many competing models of inflation, searching for the one true story of our cosmic dawn. This elegant solution to the flatness of our cosmos, however, opens a door to a far grander and more unsettling possibility. If inflation could stretch our universe into such a perfect, flat patch, what is to stop it from happening again elsewhere? The mathematics of eternal inflation suggest that once this process begins, it may never truly end. Instead, the rapid expansion becomes a self-sustaining, eternal background. Within this endlessly inflating sea, new universes can spontaneously nucleate, like bubbles forming in a vast, boiling cauldron that never cools. Each of these bubbles represents a region where, by pure chance, the inflaton field has rolled down its energy hill and settled into a stable state, just as it did in our patch. In that moment, inflation ends inside the bubble, creating a new, self-contained universe with its own distinct Big Bang. Our entire observable cosmos, with all its galaxies and stars, would be just one such bubble in an infinite, frothing multiverse. The truly radical consequence lies in the nature of the inflaton field itself. As it takes on different values in different regions, the way it decays can vary dramatically. This means the fundamental laws of physics, the strength of gravity, the masses of particles, and the very constants that govern reality could be set randomly as each new bubble universe forms. In most of these other universes, the constants might be wildly different, creating environments where atoms never form or where stars cannot ignite. They could be barren, short-lived, or governed by physics we cannot even conceive. We find ourselves in a bubble where, purely by chance, the numbers are just right for planets, for chemistry, and for life. This concept of a multiverse offers a potential explanation for the apparent fine-tuning of our universe. It is not that the cosmos was designed for us, but rather, we are a product of a cosmic lottery, living in one of the rare, hospitable pockets within an infinite and mostly inhospitable greater reality. This idea remains one of the most controversial in modern science, sitting squarely on the line between profound physics and untestable philosophy. It forces us to question the very definition of the universe and our place within a potentially limitless cosmic landscape. For inflation to truly explain our universe, it had to know when to stop. This is the graceful exit problem, a final critical act in the cosmic drama. The entire theory hinges on the inflaton field not just triggering an unstoppable expansion, but also ending it with precision, delivering a universe ready for the next chapter. Its mechanism is a slow, controlled descent. Picture the inflaton field as a ball that has been perched on a vast, almost flat plateau. Its slow, gradual roll across this plateau is what powered the exponential expansion of space. But this could not last forever. Eventually, the field reached the edge of its plateau and encountered a steep drop, the slope leading down to its true, stable energy minimum. As it began this final descent, its energy started to convert. The potential energy that had been driving the repulsive gravity of inflation was now transforming into kinetic energy. The field picked up speed, rushing down the hill until it reached the very bottom. But it did not simply come to rest. Carried by its own momentum, it began to oscillate wildly around the minimum, like a ball rapidly bouncing back and forth at the bottom of a steep valley. These oscillations are not just an abstract concept. In the language of quantum field theory, such a wildly oscillating field represents the creation of massive, unstable particles. The entire universe, now vast but largely empty after its inflationary stretching, became filled with this dense, chaotic soup of inflaton particles. Their existence was fleeting. Almost immediately, these particles began to decay, collapsing into the familiar fundamental particles we know today: quarks, electrons, photons. This cataclysmic process, known as reheating, was the moment the cold, expanded universe from inflation was flooded with a searing, intense heat. It was the true beginning of the hot Big Bang, igniting the primordial fireball that would eventually give rise to all matter. The efficiency of this reheating was everything. It had to dump just the right amount of energy, creating a universe with the immense entropy and perfect particle content we observe. If the inflaton field had gotten stuck on a ledge during its roll, or if it had decayed too inefficiently, the resulting universe would have been too cold and dilute for galaxies to ever form. Conversely, a decay that was too violent or uneven could have created monstrous defects or torn the fabric of spacetime itself. The fact that we exist in a cosmos filled with structure is a testament to the fact that our inflation did, in fact, exit with perfect grace. This final, crucial step seamlessly hands the universe from its mysterious, quantum-driven birth to the well-understood, fiery evolution of the standard cosmic story. Yet for all its explanatory power, cosmic inflation remains a theory, not an established fact. The scientific landscape is alive with competing ideas that offer entirely different visions of the cosmos's first moments. One such alternative is the cyclic model, which replaces a single beginning with an endless, rhythmic dance of creation and destruction. In this view, our universe undergoes an infinite series of big bangs and big crunches, expanding for a time before contracting back into a hot, dense state, only to rebound again. Each cycle of expansion gently smooths out the universe, much like kneading dough over and over eventually makes it uniform, thereby addressing the horizon and flatness problems without any need for a faster-than-light growth spurt. Another radical proposal is the ekpyrotic universe. This model emerges from string theory, suggesting our three-dimensional reality exists on a membrane or brane, floating in a higher dimensional space. In this scenario, our Big Bang was not a singular point of infinite density, but the aftermath of a colossal collision between our brane and a neighboring one. The immense energy of this impact heated our universe to a fiery state, while the geometry of the collision itself could have produced a smoothed and flat cosmos. Where these alternative models often encounter difficulty, however, is in replicating a specific cosmic signature, the nearly scale invariant spectrum of fluctuations in the cosmic microwave background. That delicate fingerprint of quantum jitters stretched across the sky arises naturally and elegantly from inflationary expansion. For cyclic or ekpyrotic models to produce this same pattern, they often require their own forms of fine-tuning, making their explanations less straightforward. An even greater challenge lies in the subtle polarization patterns woven into the cosmic microwave background light. Certain modes of polarization, known as B-modes, are a direct predicted relic of the primordial gravitational waves generated by inflation's violent expansion. While these signals are incredibly faint and difficult to detect, their existence is a key prediction that many alternative theories struggle to make. This ongoing competition of ideas is not a weakness of cosmology, but its greatest strength. It is the engine of scientific progress. Each rival theory pushes cosmologists to make sharper predictions and to seek more decisive observations. The ultimate goal is not to prove one idea right, but to find the model that consistently accounts for the full tapestry of data, from the largest scale structures to the faintest whispers of ancient light. The mystery of our origin is not yet settled, and the final chapter on the universe's first instant is still being written. But this elegant story of inflation pushes our understanding of physics to its absolute breaking point. The theory operates at energy scales so incredibly high that they touch the edge of meaning itself. To grasp this, we must venture into the Planck epoch, the first 10 to the negative 43 seconds of cosmic history. At this moment, the universe was so small and so energetic that the very concepts of space and time as we know them ceased to exist. This is the domain of quantum gravity, a realm where gravity can no longer be described by Einstein's smooth classical geometry. Instead, it must become a quantum force, fizzing with uncertainty and fluctuations just like the other fundamental forces. Our current tools, which treat gravity with general relativity and matter with quantum mechanics, are fundamentally incompatible here. They produce nonsensical answers, infinities that signal our equations have failed. It is like trying to use a roadmap to navigate the open ocean. The chart is simply not designed for that territory. So how did the universe emerge from this quantum gravitational fog to provide the pristine, smooth initial conditions that inflation needed to begin? This is perhaps the deepest mystery of all. Some critics argue that inflation, for all its power, merely dresses up the old problem of the initial singularity in new clothes. Instead of a single, infinitely dense point, we now have a mysterious quantum state that just happens to be perfectly set up for an inflationary expansion. It pushes the ultimate question of origins one step further back without truly answering it. Yet other theorists see a more hopeful picture. They propose that inflation acts as a cosmic attractor. Imagine a vast landscape of every possible chaotic, crumpled initial state the universe could have had. The mathematics suggests that the process of inflation itself is so powerful that it draws most of these chaotic beginnings toward the same smooth, flat, and expanding outcome. It does not matter how messy the start was, inflation cleans it up. This idea is profoundly appealing, suggesting that our orderly cosmos could have emerged naturally from a formless quantum chaos. The quest to unite inflation with quantum gravity is now the grand frontier. Theories like string theory, which envisions reality as composed of tiny, vibrating strings, or loop quantum gravity, which proposes space is woven from discrete loops, attempt to paint a picture of this first moment. They suggest possibilities where time itself is emergent, or where the Big Bang was not a beginning but a bounce from a previous cosmic phase. The interface between these ideas and inflation is a thrilling, highly speculative battleground of thought. Unlocking the secrets of the universe's true birth may not require just a new equation, but a revolution that redefines our very understanding of reality, of time, and of existence itself. This cosmic engine of acceleration may not be a one-time event. The same mysterious force that stretched our universe into existence in its first moments appears to be back at work today. We call its modern incarnation dark energy, and its discovery has forced cosmologists to ask a profound question. Could the inflaton field of the ancient past and the dark energy of our present be distant cosmic relatives, two faces of the same underlying phenomenon? Both involve a repulsive gravity, a stretching of the very fabric of space that pushes galaxies apart. The idea is incredibly tempting, suggesting a beautiful symmetry where the universe both begins and ends its story with a period of runaway expansion. Perhaps a single, all-pervading field has simply shifted its behavior over the eons, from a violent, short-lived outburst to a slow, patient dominance. This hypothetical field is sometimes called quintessence, a dynamic energy that could, in theory, connect the two most dramatic epochs of acceleration. Yet for all the elegance of this idea, the details reveal staggering differences. The energy scale of the primordial inflaton field was almost beyond calculation, a concentration of power that makes the energy of a supernova look like a faint whisper. In contrast, the energy density of dark energy today is incredibly weak and diffuse, a faint background hum that only becomes significant because it fills the vast emptiness of space. This is a difference of over 120 orders of magnitude, a number so large it dwarfs the number of atoms in the observable universe. The nature of their push is also distinct. Cosmic inflation was a transient, self-terminating event, a spectacular sprint that lasted for a mere sliver of time. Dark energy, as far as we can measure, appears to be a much more stable, persistent force, acting like a cosmological constant that could continue driving the expansion forever. This difference is captured in their equation of state, the specific relationship between their pressure and density. The inflaton field operated with a specific pressure that drove an exponential expansion. The simplest models for dark energy suggest a different, more relentless pressure, one that leads to a steadier, unending acceleration. So is the connection just a cosmic coincidence? Or is it a clue? The search for answers lies in the subtle behavior of dark energy over time. If it is truly a constant, the link to a dynamic inflaton field seems more tenuous. But if future observations reveal that the strength of dark energy is slowly changing, that it is a dynamical quintessence field, then the bridge to the early universe becomes far more plausible. We would then be looking at a single, evolving actor playing two different roles in the cosmic play, one at the beginning of time and one at its potential end. This quest unifies the entire history of the cosmos, from the first quantum tremor to the ultimate fate of all galaxies. One of the most profound predictions of inflation remains just out of reach, a ghostly signal from the dawn of time. This is the hunt for primordial gravitational waves. During that explosive period of expansion, the violent quantum jitters did not just create density fluctuations, they also sent ripples through the very fabric of spacetime itself. These are not sound waves or light waves, but literal waves of gravity, stretching and squeezing space as they travel. They are a fossil imprint of inflation's raw power. While the density fluctuations gave us galaxies, these gravitational waves would leave their own unique signature on the oldest light in the universe. The key to finding them lies in a specific pattern woven into the polarization of the cosmic microwave background. Light can vibrate in certain directions, and the primordial plasma imprinted a specific curl-free pattern onto the sky, known as E-mode polarization. This was expected, but the passage of primordial gravitational waves would have twisted this light, adding a distinct curling pattern known as B-mode polarization. Finding this curl is the ultimate goal. It is considered the smoking gun for inflation because its strength is directly tied to the energy scale of the event. A detection would not just confirm that inflation happened, it would tell us exactly how powerful it was, giving us a direct measurement of the universe's energy when it was a tiny fraction of a second old. This would be a window into physics at energies 1 trillion times higher than anything our particle colliders can reach, brushing against the Planck scale itself. The quest for this signal drives some of the most ambitious experiments on and above our planet. Telescopes like BICEP and the Keck Array are stationed at the South Pole, where the cold, dry air offers a crystal-clear view of the cosmic microwave background. They stare at a single patch of sky for years, building up an exquisitely sensitive map of its polarization. The challenge is monumental. The signal they seek is incredibly faint, a whisper nearly drowned out by louder cosmic static. The twisting pattern they hunt for can be mimicked by interstellar dust within our own galaxy, or by the gravitational lensing of the E-modes themselves by later cosmic structures. Teasing apart the true primordial signal from these foreground contaminants is a Herculean task of data analysis. The potential reward, however, is a revolution in our understanding. A confirmed, unambiguous detection of these primordial B-modes would be a Nobel Prize-winning discovery, a direct message from the inflationary epoch that would cement our story of cosmic origins. It would be the final, crucial piece of evidence, allowing us to move from a compelling theory to a detailed history of the universe's very first moment. This vast theoretical landscape reveals a cosmos born not from a single, simple recipe, but from a whole menu of possibilities. The inflaton field could have rolled down its energy hill in a multitude of ways, and each path corresponds to a different model of inflation. In chaotic inflation, the field starts from a wildly high energy point on a simple slope, tumbling down to create our universe from a random, initial state. New inflation, by contrast, imagines the field getting temporarily stuck in a false vacuum on a plateau before its slow roll begins. Then there is hybrid inflation, where two fields work in concert, one driving the expansion and the other triggering its end. These are just a few of the hundreds of proposed models. They differ in crucial details like how long the inflationary period lasted, how violently the field oscillated during reheating, and most importantly, the precise character of the quantum seeds they planted. Each model leaves a distinct fingerprint on the cosmos, predicting a slightly different pattern for those primordial density fluctuations and gravitational waves. This incredible diversity is both the framework's greatest strength and its most significant challenge. On one hand, it demonstrates the remarkable flexibility of the core idea that a period of accelerated expansion can solve the major cosmological puzzles. When one model faces a conflict with data, theorists can often adjust the shape of the inflaton field's potential energy landscape, crafting a new variant that fits the observations. This adaptability has allowed the inflationary paradigm to survive and evolve for decades. Yet this very flexibility also opens the theory to criticism. If any observational result can be accommodated by simply switching to a different model, how can we ever truly prove inflation wrong? A theory that can explain almost any outcome risks explaining nothing at all. It becomes difficult to falsify, a key requirement for a robust scientific idea. This is where the painstaking work of observational cosmology becomes so vital. The goal is no longer merely to confirm that inflation happened, but to rule out vast swaths of this theoretical landscape. Scientists are forensic experts, examining the cosmic crime scene with ever sharper tools. They measure two key parameters with exquisite precision. The first is the spectral tilt, that tiny deviation from perfect scale invariance in the cosmic microwave background. The second is the tensor-to-scalar ratio, which measures the relative strength of gravitational waves compared to density fluctuations. Each inflationary model makes a specific prediction for this pair of numbers, placing it at a unique point on a master graph. As our telescopes gather more data, they shrink the allowed region on this graph, systematically eliminating entire families of models. We are slowly cornering the truth, using the universe's own ancient light to guide us through the maze of possibilities. The existence of this sprawling landscape is a humbling admission. It reflects our current ignorance about the fundamental physics that must ultimately govern inflation. We are describing the cosmic symptoms with brilliant success, but the underlying disease, the true nature of the inflaton field and its origin in a theory of quantum gravity, remains a mystery. Yet for all its power, inflation presents us with a profound and unsettling silence. The theory masterfully describes the universe from about 10 to the negative 36 seconds onward, but it draws a stark, impenetrable curtain over what came before. What was the initial condition that sparked this entire cosmic chain reaction? This is a deep form of the information paradox. Imagine trying to trace the origin of a single, perfectly smooth wave in the middle of the ocean. The wave itself is beautiful and predictable, but the complex storm system that created it, thousands of miles away, has left no trace on its form. Inflation acts in a similar way, but with cosmic consequences. The phenomenal stretching of space during that brief epoch did more than just smooth out the cosmos. It effectively erased it. Any prior structure, any wrinkles, any information about what the universe was like before inflation was diluted to nothingness by the incredible expansion. The universe was essentially reset to a blank, uniform slate, so we are left with fundamental questions that may be forever beyond our reach. Did our universe spontaneously burst into existence from a random quantum fluctuation in a deeper, more fundamental vacuum? Or was there a previous cosmic cycle, a great contraction that culminated in a bounce, giving birth to our expanding reality? The most radical possibility is that the question itself is meaningless. If time, as we understand it, was born alongside our universe in the Big Bang, then the concept of a before may be as nonsensical as asking what is north of the North Pole. Our physics, built upon the continuum of space and time, simply breaks down at that point. This leads some scientists to a sobering conclusion. Cosmology, as a science based on observation and deduction, might only be able to provide a complete history of the cosmos from the start of inflation onward. Everything before that moment may be permanently lost to us, a secret the universe is designed to keep. This is not a failure of our theories, but a humbling reminder of the ultimate boundaries of our knowledge, framing our entire cosmic story with an eternal and profound mystery. The immense energy of the infant cosmos did more than just stretch space. It unified the very laws of physics. In that first fleeting moment, the fundamental forces we know as separate today were fused into a single, perfect symmetry. The strong nuclear force that binds atomic nuclei, the weak force governing radioactive decay, and the electromagnetic force that orchestrates light and chemistry were all indistinguishable facets of one grand, unified force. This was a state of ultimate simplicity, a cosmic oneness where the rules were seamless and whole. Then came the great unraveling. As the universe expanded and cooled during its inflationary growth spurt, it underwent a profound transformation, a series of cosmic phase transitions not unlike water freezing into ice. In its liquid state, water is perfectly symmetric, looking the same in every direction. But when it crystallizes into ice, it picks a specific orientation for its molecular structure, breaking that initial symmetry. The universe did the very same thing. With each drop in temperature, a piece of the unified force broke away, freezing out into the distinct interactions we recognize today. The inflaton field, the very engine of the universe's expansion, may have been the cosmic catalyst for this process. It could be deeply related to other fundamental fields, like the Higgs field that gives particles their mass. The moment the inflaton field rolled down its energy hill to end inflation, it may have triggered the very symmetry breaking that defined the forces of nature. The colossal energy released as these forces separated from their unified state could have been the driving force behind the violent reheating that filled the universe with the hot plasma of the Big Bang. This elegant connection forms a central pillar of modern physics, weaving together the story of the impossibly large with the rules of the infinitesimally small. We can never build a particle collider powerful enough to directly recreate the energies of grand unification, a scale trillions of times more powerful than our best machines. But we are living inside the wreckage of that primordial event. The cosmos itself is our laboratory. By studying the detailed fingerprint of inflation imprinted on the sky, the specific pattern of the quantum seeds it planted, we are indirectly testing theories of physics at energies so extreme they are otherwise forever beyond our grasp. The universe's first moment holds the key not just to our cosmic origin, but to the final, unified theory of everything. Hidden within the cosmic microwave background is a far more elusive echo from an even earlier time. This is the cosmic neutrino background, a ghostly sea of particles that has been streaming through the universe since it was just 1 second old. These neutrinos were forged in the immense heat of the reheating era, the moment when the inflaton field decayed and flooded the cosmos with its energy, creating the primordial fireball. For that first second, the universe was so dense and hot that even these phantom particles were trapped, constantly colliding with protons, electrons, and photons. But as the cosmos expanded and cooled, a pivotal moment arrived. The density dropped to a point where neutrinos, which barely interact with anything, could finally escape. They stopped colliding with matter and began streaming freely across the universe, never to be significantly disturbed again. This event, known as neutrino decoupling, created a fossil imprint that has lasted for over 13 billion years. This cosmic neutrino background is the universe's oldest known fossil. predating even the cosmic microwave background by several 100,000 years. It is a snapshot of the cosmos at 1 second old, a direct messenger from the aftermath of inflation's end. Yet detecting this messenger is a monumental challenge. Neutrinos are the most elusive of all known particles, able to pass through light years of lead without a single interaction. Billions of them are streaming through your body every second, completely unnoticed. This same property that makes them so ghostly also makes their ancient background incredibly difficult to observe directly. We have strong indirect evidence for its existence, as its gravitational influence is woven into the large-scale structure of the universe and the precise power spectrum of the cosmic microwave background. But capturing a definitive, direct signal remains one of the great unsolved problems in physics. The potential reward, however, would be a new window into the dawn of time. The temperature and distribution of these primordial neutrinos are not arbitrary. They carry encoded information about the exact conditions during the reheating phase. By studying this background, we could measure the temperature of the universe just after inflation ended, providing a crucial benchmark for the energy scales involved. It could reveal details about the particle interactions that were dominant in that first second, and even offer clues about physics beyond our current standard model, such as the exact mass of the neutrino itself. The hunt for this ghostly echo pushes the very limits of our technology, requiring detectors buried deep underground to shield them from any other cosmic noise. To hear this whisper from the end of inflation would be to listen to the universe taking its first stable breath, a faint signal holding the secrets of our fiery beginning. This perfect cosmic blueprint, however, holds a few strange and unsettling blemishes. When we look at the most detailed maps of the cosmic microwave background, we find features that simply should not be there according to the simplest models of inflation. One of the most puzzling is known as the axis of evil. This is not a cosmic antagonist, but a startling alignment of the largest warm and cold spots in the ancient sky. These colossal features appear to be mysteriously coordinated along a particular line, a preferred direction in the cosmos that seems to point, eerily, toward our own solar system. This creates a kind of celestial axis that defies our most fundamental assumption about the universe. The cosmological principle states that the universe, on large scales, should look the same in every direction. It should have no center, no edge, and certainly no special axis. The existence of such a direction is like discovering that all the continents on Earth are subtly aligned along a single, invisible line running through your own backyard. The statistical probability of this happening by pure chance in an isotropic universe is incredibly low, sparking intense debate among cosmologists. So what does this mean for our story of cosmic inflation? Could this be the first real crack in the elegant facade of our standard model? One possibility is that this is just a cosmic mirage, a statistical fluke in the one universe we are able to observe. With only one sky to map, we cannot know for sure if this alignment is truly strange or if we are simply seeing a pattern in the cosmic static, much like seeing a face in the clouds. Yet the persistence of this signal across different satellite missions makes that explanation feel increasingly strained. Another, more thrilling possibility is that the axis of evil is a fossil, a relic from a time before inflation. Perhaps the inflationary expansion was not quite powerful enough to completely erase all the primordial wrinkles. A tiny piece of pre-inflationary structure, a kink in the fabric of spacetime from the universe's very first quantum instant, might have survived the great stretching. This would mean our observable universe is not a perfectly representative sample, but a slightly skewed patch that retains a memory of its chaotic birth. Or perhaps the explanation requires entirely new physics, suggesting the overall shape of the universe is more complex than we thought. Maybe the cosmos has a non-trivial topology, a connected geometry where space wraps around itself in a way that creates large-scale patterns we are only beginning to perceive. These anomalies are not failures of our science, but its guiding lights. They are the places where our current models strain and crack, pointing toward a deeper, more complete theory of the primordial universe. They are a humbling reminder that nature always has another secret to reveal, and that the final chapter on our cosmic origins is still being written in the sky. This infinite cosmic lottery presents a profound challenge to the very logic of prediction. If eternal inflation generates a limitless number of bubble universes, then every conceivable combination of physical constants and laws must exist somewhere, not just once, but an infinite number of times. An infinite number of universes will have stars and planets like ours, while an infinite number will be cold, empty voids. When every possible outcome occurs infinitely, the concept of probability seems to break down completely. How can we say our universe is likely or unlikely if its conditions are replicated endlessly across the multiverse? This is the notorious measure problem, a puzzle that strikes at the core of whether the multiverse can ever be a true scientific theory. The issue is not the existence of other universes, but how to count them in a meaningful way. Without a method to compare the number of hospitable universes to the number of inhospitable ones, we cannot explain why we find ourselves in a world that allows for life. It would be like trying to determine if red marbles are common or rare in an infinite bag containing every color of marble in infinite quantities. Simply reaching in tells you nothing about the proportions, because your hand will always find an infinite number of every type. Scientists have proposed various mathematical tools to tackle this. One approach is to consider only a finite causal patch, the part of the multiverse we could ever possibly observe, and use that as our sample. Another method involves a geometric cutoff, imagining a finite sphere within the infinite multiverse and counting the universes inside it, then watching what happens as the sphere's size is allowed to grow toward infinity. The hope is that a stable ratio emerges, a consistent percentage of universe types that holds true regardless of the sphere's exact size. Yet these are technical fixes for a deeply philosophical dilemma. If we cannot define a reliable measure, then the multiverse hypothesis loses its power to explain the apparent fine-tuning of our cosmos. It would retreat from testable science into the realm of untestable metaphysics, a beautiful story without a way to verify its truth. The quest to solve the measure problem is therefore essential for anyone who wants to take the idea of a multiverse seriously. It is the final, formidable barrier between a captivating speculation and a robust framework for understanding our place in a truly cosmic landscape. The profound legacy of inflation is written in the atoms that make up our bodies, yet this very existence poses one of the most fundamental riddles of all. Our universe is composed almost entirely of matter, with antimatter appearing only fleetingly in particle collisions or cosmic rays. According to everything we know, the Big Bang should have created equal amounts of matter and antimatter. And when a particle of matter meets its antimatter twin, they annihilate in a flash of pure energy. So why did this not happen? If the cosmos began with perfect symmetry, all matter and antimatter should have mutually destroyed one another, leaving behind a universe filled with nothing but light. The fact that we are here, that stars and planets exist at all, means something must have broken that perfect symmetry, leaving behind a tiny, vital surplus of matter. This is the puzzle of Baryon asymmetry. The stage for this cosmic imbalance was set during the final moments of inflation. As the inflaton field rolled down its energy hill and began to violently oscillate, the universe entered the reheating phase. This was not a gentle warming but a cataclysmic burst of particle creation, a seething cauldron where the laws of physics could operate in their most extreme form. Within this frenzy, certain particle physics theories suggest that a crucial rule was broken. This rule is known as CP symmetry. In simple terms, CP symmetry means that the laws of physics should treat matter and antimatter as perfect mirror images. But in the incredible heat of reheating, processes that violate this symmetry could have occurred. Think of it like a factory that is supposed to produce equal numbers of left-handed and right-handed gloves. Due to a subtle flaw in the machinery, it produces just a few more left-handed gloves for every billion pairs. In the early universe, this flaw was a fundamental interaction that, under those specific hot and dense conditions, favored the production of matter particles over antimatter particles. For every 1,000,000,001 particles of matter created, only 1 billion particles of antimatter were made. The subsequent annihilation was nearly total, wiping out all the antimatter and the matching billion particles of matter. But that 1 in a billion surplus of matter was left behind. That minuscule excess is the source of every atom, every star, and every galaxy we see today. This entire process, known as baryogenesis, links the grand cosmic stage set by inflation directly to the existence of our material world. Without that brief window of violent particle creation and the subtle breaking of a fundamental symmetry, the universe would be a vast, dark, and empty sea of radiation. Inflation did not create the matter asymmetry itself, but it created the pristine, expanding arena where this delicate physics could play out, ensuring that the cosmic story had something to build with. This cosmic stretching forces us to confront a profound and unsettling limit to our knowledge. The very quantum fluctuations that seeded all galaxies were magnified from an impossibly small scale, a scale where our understanding of physics simply dissolves. During that exponential expansion, wavelengths were stretched from a size far smaller than the Planck length to one that spans the observable universe. The Planck length is the ultimate lower limit in physics, a distance so tiny that the very concepts of space and time lose their meaning. At this scale, quantum gravity is thought to create a foaming, turbulent sea of spacetime, a realm where our trusted equations of general relativity and quantum field theory are no longer your reliable guide. The Transplanckian problem asks a deeply uncomfortable question. Can we truly trust the inflationary story when its most crucial prediction, the origin of all structure, relies on physics applied to a domain where that physics almost certainly fails? It is like using the rules of continental drift to describe the movement of a single grain of sand. The framework is not designed for that, and the results, while perhaps numerically convenient, may be completely divorced from reality. The fluctuations we celebrate in the cosmic microwave background, the blueprint for our entire cosmos, may have been born in a territory we cannot yet map. Some theoretical work suggests that effects from a true theory of quantum gravity, such as modified dispersion relations that change how waves behave at those extreme energies, could have subtly altered the pattern of these seeds. Perhaps the universe's fingerprint carries a faint scar from this Transplanckian realm, a tiny deviation from the predictions of standard inflation that our telescopes have not yet been sensitive enough to detect. This problem does not invalidate inflation, but it frames our entire understanding with a fundamental caveat. It reminds us that we are likely seeing only a shadow of the true, deeper mechanics that sparked existence, a glimpse of a cosmic dawn whose first instance remains shrouded in a mystery our current science cannot penetrate. The next generation of cosmic observatories is already taking shape, designed to listen for the faintest whispers from the beginning of everything. projects like the Simons Observatory and the even more ambitious CMBS-4 are not merely upgrades, they are leaps into a new realm of sensitivity. Their mission is to map the cosmic microwave background's polarization with a clarity we have never before achieved. The primary target is that ghostly curl in the polarization, the B-mode pattern that is the direct signature of primordial gravitational waves. Detecting this signal would be like finding the original cosmic fingerprint, confirming not just that inflation happened, but revealing its raw power. Yet these observatories will do so much more. They will measure the temperature fluctuations of the ancient light with such fine resolution that they can test the inflationary blueprint to its limits. They will scrutinize the spectral index, that tiny tilt in the pattern of fluctuations, and even search for its running, a potential change in that tilt across different scales. These subtle details are like the fine brushstrokes on a masterpiece, each one pointing to a specific model of how the inflaton field rolled down its energy hill. A single, precise measurement here could eliminate entire families of inflationary theories, cornering the true story of our cosmic dawn. Another critical search is for non-Gaussianity. The simplest models of inflation predict that the quantum seeds should follow a bell curve distribution, a signature of random, non-interacting fluctuations. But if future data reveals a deviation from this simplicity, if the statistics show subtle correlations, it would be a revolution. It would mean the inflaton field was not rolling in isolation, but was interacting with other fields in a complex cosmic dance during those first moments. This would open a window into physics at energies far beyond the reach of any particle collider. And then there are the anomalies, those strange features like the axis of evil that do not quite fit the standard story. Are they mere statistical flukes, cosmic mirages in the one sky we can observe, or are they real clues to a deeper, more complex origin? The incredible data from these next-generation experiments will provide the final word, either smoothing them away as noise or confirming them as cracks in our current model, pointing the way to a new physics. The next decade promises to be a golden age for cosmology, where the ancient light from the universe's infancy may finally yield the definitive answers we have been seeking for decades. We can never build a particle accelerator large enough to recreate the universe's first moment, yet physicists have found a way to bring the cosmos into the laboratory. They use analog systems, ingenious setups that mimic the physics of inflation in a controlled tabletop environment. One of the most fascinating of these involves Bose-Einstein condensates, a state of matter where atoms are cooled to near absolute zero and behave as a single quantum wave. In this superfluid, researchers can create sonic horizons. Sound waves traveling through the condensate are like light waves in our expanding cosmos, and they find they cannot cross a certain boundary if the fluid is flowing faster than the speed of sound. This is a direct parallel to the event horizon of a black hole or the cosmological horizon of our universe. In these experiments, scientists have observed the spontaneous creation of phonons, the quantum particles of sound, from the vacuum. This is a laboratory version of the mechanism that, during cosmic inflation, stretched quantum fluctuations into the seeds for galaxies. It is a stunning validation that the bizarre process of generating something from nothing is a fundamental feature of quantum fields, whether in a vat of supercold atoms or in the newborn universe. Another approach manipulates light itself. Using specially designed optical fibers or metamaterials, physicists can engineer an effective metric for light, making it behave as if it were traveling through an expanding or curved spacetime. In these systems, the light experiences an analog of the Hubble expansion, allowing researchers to study how quantum fluctuations would evolve under such conditions. While these are not miniature Big Bangs, they are powerful testing grounds. They allow us to probe the intricate marriage of quantum field theory and general relativity in a setting where we can tweak the parameters and watch what happens. This hands-on experimentation complements another frontier of discovery, the realm of pure computation. Supercomputers now run complex simulations that model the behavior of the inflaton field itself. These are not simple animations, they are numerical solutions to the full equations governing a scalar field in an expanding universe. Researchers can set up virtual universes with different initial conditions, watch as inflation unfolds, and see what kind of density fluctuations and gravitational waves are produced. They can test if certain models of inflation lead to a graceful exit or if they produce catastrophic defects like cosmic strings. These digital laboratories provide a crucial bridge between abstract theory and observable reality, suggesting new signatures that our telescopes might one day detect. Together, these lab-based analogs and computer simulations form a new branch of experimental cosmology. They represent a profound shift in how we explore our origins, not by looking deeper into space, but by recreating the underlying physics of spacetime itself on a human scale. Cosmic inflation may have given us not just a universe but time itself. By weaving the entire observable cosmos from a single, causally connected patch, it solved the horizon problem and created a shared history, making a universal now possible across vast distances. This common causal past means the events we see in opposite corners of the sky were once in touch, allowing for the synchronized timeline we take for granted. Yet this tidy picture shatters if the multiverse is real. Beyond our bubble of reality, other universes may be governed by entirely different laws, where time could flow in ways we cannot comprehend or not exist at all. The single, linear timeline of our cosmic story becomes a provincial notion, relevant only within our local pocket of existence. This leads to an even more radical thought. The incredible power of inflation to produce a universe like ours from almost any chaotic starting point suggests that a specific, finely tuned beginning might be unnecessary. Perhaps the cosmos did not need a precise initial moment to kick everything off. Some physicists speculate that inflation is the very mechanism that conjured time from a timeless state, a primordial quantum realm where the concepts of before and after had no meaning. In this view, the Big Bang was not the beginning of time, but the moment time as we know it emerged, crystallizing from a more fundamental, atemporal reality. These are not just scientific questions, but deep philosophical probes into the nature of existence and causality. The mystery of cosmic inflation forces us to confront the possibility that the very stage upon which reality plays out is not a fixed background, but a dynamic, emergent property of the universe's first and most dramatic transformation. These profound ideas remain trapped behind a wall of intuition. How do you explain the stretching of spacetime itself to someone who has never questioned the rigid stage beneath their feet? We are trying to describe a reality where the very rules of distance and speed are rewritten, using a language evolved for a world of solid objects and fixed horizons. The most effective tools we have are analogies, but each is a compromise. The expanding raisin bread loaf beautifully illustrates how galaxies recede not by moving through space, but because the dough between them grows. Yet it fails to capture the sheer, violent speed of inflation or its origin in a quantum realm. The stretching rubber sheet conveys the warping of gravity, but not the spontaneous creation of space. The challenge is to use these stories as stepping stones, not final destinations, always clarifying where the metaphor breaks down. We must be clear about the evidence, the rock-solid observations like the cosmic microwave background's flatness and fluctuations that inflation so elegantly explains. We must distinguish this from the well-supported theoretical framework of the inflaton field. and separate both from the more speculative, though thrilling, ideas of a multiverse. This careful communication is not just about public education, it is about building a bridge of shared wonder. The story of cosmic inflation is a triumph of human reason, a demonstration that through mathematics and relentless curiosity, we can decode the universe's first whisper. It invites everyone to look up at the night sky and comprehend that the vast, glittering expanse is the magnified echo of a quantum tremor. This understanding does more than fill textbooks. It fuels the public imagination and fosters support for the pure, fundamental science that drives our species forward. In sharing this grand mystery, we participate in one of humanity's noblest quests, the unending adventure to understand our place in a cosmos far stranger and more magnificent than we ever thought possible. A truly scientific idea must stand on the edge of a knife, ready to be cut down by evidence. This is the principle of falsifiability, and it is here that cosmic inflation faces one of its most serious challenges. The theory's incredible adaptability, with its landscape of hundreds of models, can appear to be a weakness. If one version of inflation is contradicted by an observation, could theorists not simply retreat to a different model with a slightly differently shaped energy hill? This flexibility, some critics argue, makes inflation not a single testable theory, but a protected paradigm, one that can always be adjusted to fit the data. It is a valid and vital criticism that strikes at the very heart of the scientific method. How can we ever prove inflation wrong if it can explain almost any outcome? A theory that accounts for everything ultimately explains nothing. Yet this view overlooks the robust, concrete predictions that form the bedrock of the inflationary paradigm itself. The core idea makes several claims that are absolutely falsifiable. It predicted a geometrically flat universe long before our most precise measurements confirmed it. It demanded a nearly scale invariant spectrum of primordial fluctuations, a specific fingerprint that has been spectacularly verified in the cosmic microwave background. Its most dramatic prediction, the existence of primordial gravitational waves imprinted as a curling B-mode pattern in that ancient light, remains a decisive test. The ongoing, painstaking search for that signal is not a vague fishing expedition. It is a direct assault on the theory's heart. If next-generation observatories, after exhausting every possible source of interference, conclusively find no evidence of these primordial B-modes, they would rule out a vast and popular swath of the inflationary landscape. The simplest and most elegant models would fall. Similarly, the hunt for non-Gaussianity in the cosmic microwave background is a critical probe. The standard story of a simple, slowly rolling inflaton field predicts that the quantum seed should be random and uncorrelated, following a bell curve distribution. But if our maps of the sky ever reveal a clear, statistical deviation from this pattern, a signature of interactions between fields in the early universe, it would invalidate that simple picture and force a major revision. This is the dynamic, sometimes messy, process of science in action. Theorists propose a range of ideas, each making subtle but different predictions. Observers then build ever better instruments to test those predictions, narrowing the field of viable options. The healthy skepticism and rigorous criticisms leveled at inflation do not weaken it. They strengthen the entire endeavor, forcing everyone to sharpen their arguments and seek more definitive evidence. This relentless pressure ensures that inflation remains a living, breathing scientific theory, continually evolving and being refined, rather than settling into an untouchable and unquestionable story. The horizon and flatness problems were like stubborn cracks in the foundation of cosmology, and it was a young physicist named Alan Guth who found the tool to fix them. In 1980, Guth had a moment of profound insight, realizing that a brief period of exponential expansion could iron out the universe's wrinkles. He called this idea inflation. His original model, now known as old inflation, was a brilliant starting point. It proposed that the universe got stuck in a false vacuum state, and its energy drove a fantastic, faster-than-light expansion that smoothed and flattened the cosmos. But Guth soon identified a critical flaw. In his model, the phase transition that ended inflation, the bubble nucleation, happened too unevenly. The universe would have become a messy, inconsistent froth of bubbles, not the uniform expanse we observe. This was the graceful exit problem, and it was a serious one. Yet instead of discarding the idea, the scientific community saw its potential. Guth's paper was not an end, but a magnificent beginning. It ignited a firestorm of research, challenging other brilliant minds to solve the puzzle he had laid out. Soon, physicists like Andre Linde, Paul Steinhardt, and Andy Albrecht stepped forward with refined models. They developed what is called new inflation, where the inflaton field rolls slowly down a gentle plateau, allowing for a much more uniform and graceful end to the explosive growth. Linde then took this a step further with his concept of chaotic inflation, suggesting that the initial conditions for this expansion could arise naturally from a random, chaotic state. This was science at its best. A powerful new idea was proposed, its weaknesses were openly identified, and a collaborative process of refinement began, building a stronger, more robust theory. For over 4 decades, this framework has dominated our cosmic origin story, a testament to the power of a single, elegant idea to reshape our entire understanding of reality and open up vast new fields of inquiry. This brief but spectacularly violent event was the turning point for all of cosmic history. To truly grasp its importance, we need to see where it fits in the grand timeline of everything. Cosmic inflation is the essential foundation, the crucial first chapter that set the stage for every single event that followed. The story begins in the unknowable chaos of the Planck epoch, before time itself had a stable meaning. Then, at the impossibly early age of 10 to the negative 36 seconds, the inflaton field took command, for a mere sliver of time until about 10 to the negative 32 seconds, the universe underwent its phenomenal growth spurt. When that expansion ended, it triggered the cataclysm of reheating, dumping all that stored energy into the cosmos and igniting the true hot Big Bang. From that fiery dawn, the well-established sequence of cosmic evolution could begin. In the first few minutes, nucleosynthesis forged the lightest atomic nuclei, hydrogen and helium, from the primordial soup. For hundreds of thousands of years, the universe remained a hot, opaque fog of plasma, until it cooled enough for electrons to combine with nuclei in the event we call recombination. This is the moment the cosmic microwave background was released, that first flash of light we still detect today. With the universe now transparent, gravity could finally get to work on the seeds inflation had provided. Over billions of years, those subtle density fluctuations collapsed into the first stars, which gathered into the first galaxies, and eventually led to the planets and the intricate chemistry that allows us to exist. Every single step in this epic chain relies on the initial conditions established during inflation. It is why the universe is so vast and geometrically flat, providing the room for this long evolution to unfold. It is why the cosmos was so perfectly smooth, allowing for a consistent starting point, and most importantly, it provided the subtle imperfections, the blueprint without which the universe would have remained a formless, thin gas. Without that initial quantum tremor stretched to cosmic proportions, there would be no galaxies, no stars, no planets, and no us. Viewing inflation in this context transforms it from a theoretical curiosity into the pivotal event that made our material reality possible. It was the moment a formless quantum blur was forged into a coherent universe, perfectly prepared for the long journey toward complexity and life. The inflaton field remains a ghost in our cosmic equations. We have given it a name and described its actions, but its true nature is one of the deepest enigmas in physics. Is it a fundamental particle, a new type of force, or perhaps a composite field woven from the fabric of something more profound? We simply do not know. This fundamental lack of understanding extends to the very trigger for the entire event. What was the initial spark that set the inflaton field into motion, pushing the universe from a quantum state into its epic expansion? The theory describes the how with breathtaking precision, but the ultimate why remains a profound silence. And then there is the multiverse, a concept that flows so naturally from the mathematics of inflation. Is our cosmos truly just one bubble in an infinite, frothing cosmic foam? This idea is as thrilling as it is untested, sitting squarely on the boundary between scientific prediction and philosophical speculation. The hunt for primordial gravitational waves continues to be one of the most urgent quests in cosmology. That faint, curling pattern in the cosmic microwave background is the definitive signature we need to confirm inflation's most violent moments. Its detection would be a direct line back to the universe's first instant, but its absence would force a major and dramatic rethink of our entire origin story. We are also left wondering about the final act of this cosmic drama, the moment of reheating. How exactly did the energy of the inflaton field convert into the searing hot soup of the Big Bang? The process is outlined in theory, but the precise particle interactions, the specific channels of decay, remain a blur. This is not a minor detail. The efficiency of reheating determined the entire particle content and temperature of the newborn universe, setting the stage for everything to come. Perhaps the most tantalizing connection is the one that remains purely speculative, the potential link between the inflaton field and dark energy. Could the force that started it all be related to the force that is ending it? Both drive an accelerated expansion of space, but their energy scales are separated by a gulf so vast it defies comprehension. Bridging that chasm would require a revolution in physics. And that points to the ultimate limitation of our current knowledge. We have yet to successfully weave the story of inflation into a complete theory of quantum gravity. Our equations work brilliantly until we approach the Planck epoch, the very moment of creation, and then they shatter into nonsense. This tells us that the full truth of cosmic inflation is locked within a deeper theory of reality, one that unites the very large with the very small. These are not failures of the theory, but the signposts for the next great adventure in science. Each unsolved mystery represents a frontier, a question that drives the construction of more powerful telescopes and the development of more profound theories. The pursuit of these answers will not just refine our model of inflation, it will almost certainly lead us to new physics, to a deeper understanding of the universe that will reshape our place within it. The greatest discoveries are not the ones we have already made, but the ones that still lie in the dark, waiting for a glimmer of light. Our journey through the mystery of cosmic inflation reveals a cosmos born from a fleeting, impossible growth spurt. We have traced the path from a quantum whisper to a cosmic roar, from a realm smaller than a proton to an observable universe of staggering scale. This single, elegant idea solved the great puzzles of the Big Bang, ironing out its wrinkles and flattening its geometry, while simultaneously planting the seeds for every galaxy and star. It even suggests our entire reality may be just one bubble in an infinite, frothing multiverse. the evidence is etched into the ancient light of the cosmic microwave background, a fossilized blueprint that matches the predictions with breathtaking accuracy. Yet the final confirmation awaits, hidden in the ghostly curl of primordial gravitational waves. The ongoing hunt for this signal promises to measure the raw energy of creation itself. So many questions persist, of course. The true identity of the inflaton field remains a ghost in the machine. The initial trigger is still shrouded in the fog of quantum gravity, and the potential link to dark energy is a tantalizing, unresolved thread. But these are not failures, they are the frontiers. The story of cosmic inflation stands as a monumental triumph of human curiosity, a testament to our ability to decode the universe's first moments from the faintest whispers in the void. It teaches us that the grandest structures are born from the smallest fluctuations, and that the very expansion of space holds the deepest secrets of our origin. So the next time you gaze at the night sky, remember that you are not just looking at distant points of light. You are witnessing the magnificent, stretched-out echo of a quantum tremor, a cosmic story more wondrous than any we could have invented. The mystery endures, inviting us all to keep looking up and wondering what else the cosmos has to reveal.